Water is an important resource required by all plants. It functions in plants as a solvent, a heat regulator, and as a biochemical reagent in photosynthesis. It is a major modifier of growth. Its availability or non-availability during certain phases of growth can seriously affect survival, growth rate, and the ultimate size of the plants. Properly irrigated stock will be larger, healthier, and more vigorous. Therefore, an understanding of irrigation practices is essential to growers, particularly those who produce plants in containers. I'm Dr. DeBusk, and this video will discuss the irrigation systems, techniques for calculating proper water usage, cyclic irrigation, and monitoring. Irrigation is usually a daily event during the growing season for container plants. Most growers use well or surface water as their supply. For surface water sources, it is suggested that 1 acre-inch or 27,000 gallons of water be maintained in storage for each acre of land under container production. While less than 1 inch per acre per day may be needed, the additional volume of water in storage will compensate for losses during periods of excessive heat and drought. Overhead sprinkler systems are used widely on smaller containers, but applications by this method usually result in excessive water application. One strategy to minimize water losses is to use cyclic irrigation, multiple applications of small amounts. For larger nurseries, another strategy may be to incorporate variable speed pump motors, which will save electricity and water by allowing individual zones to be irrigated without affecting pumping pressure. Compared to overhead irrigation, micro-irrigation of container plants can result in less water applied. Savings in equipment costs can be realized because micro-irrigation systems require smaller pumps and pipe sizes. However, micro-irrigation systems have higher initial and maintenance costs, and overhead irrigation may still be needed to relieve heat stress during high temperature months. Maintaining micro-irrigation systems is a time-consuming process since a shortage of water to a container plant can cause permanent decline in a matter of days. Micro-irrigation systems can become clogged or the emitter removed or chewed through by animals such as rabbits and squirrels. It often requires the dedication of one or several individuals each week to check the plants for signs of wilting. Several different sub-irrigation systems have been developed for nurseries. Some include capillary map and flood systems, ebb and flow benches, and trays or benches with liners. All rely on the principle of capillary action to move water upwards through the container substrate. Sub-irrigation systems can conserve water and reduce nutrient loss, particularly when nutrients are supplied in irrigation water that is reused. A central potting location is common for nurseries that produce container plants outdoors or under shade. At this location, containers are filled with potting substrate and plants transplanted, after which they are transported to a watering station where plants are irrigated thoroughly. Irrigation water is applied rapidly with high-volume, shower-like nozzles that are elevated above the plants. Plants are passed through the water station several times. A large volume of water is applied to settle the potting substrate around roots and ensure that it achieves maximum water holding capacity. Water not retained by the container becomes runoff in addition to the water that fell between the containers. Soluble nutrients from the potting substrate along with extraneous fertilizer granules can be readily transported in this runoff. It is critical to ensure all irrigation water is applied uniformly and in the correct amount to meet plant needs. Wind can reduce uniformity, so if wind frequently interferes with water distribution, consider creating a windbreak. For overhead irrigation, the irrigation uniformity should be calculated in order to calibrate the system. The irrigation water distribution uniformity, or DU, is the average volume for 1/4 of the cups, with the smallest volumes divided by the average volume of all the cups and multiplied by 100 to convert it to percent. For example, if 60 cups were used and the average of 15 cups with the smallest volumes was 42 milliliters and the average volume in all 60 cups was 50 milliliters, then the DU is 84%. Distribution uniformity should be 80% or higher. You should determine the irrigation uniformity at least every 3 years for each type of irrigation system and maintain these records. The amount of irrigation water needed per application will depend on container size, potting substrate water content, plant spacing, weather conditions, and the ability of the plant's canopy to capture irrigation water that falls between containers. To determine how much effect that last factor of irrigation application efficiency has, you can calculate the irrigation capture factor. You can see from the table that plants vary considerably in their ability to capture water and navigate it into the pot. The irrigation capture factor is the amount of water captured by a container plant relative to the water captured by the same container without a plant. It is calculated as the plant weight gain through the addition of irrigation divided by the weight of water in plastic-lined containers. If the capture factor is greater than 1, then the plant funnels water into the container and the amount of irrigation can be reduced. For the podocarpus with a capture factor of 3.16 in a 16-inch container, you can determine the amount of time the irrigation runtime can be decreased by dividing 100 by the capture factor and subtracting it by 100%. In this case, the runtime can be decreased by 68%, which is quite significant. Considering these application factors and adjusting the irrigation amount, growers can manage their water more efficiently. One way to determine if the correct amount of water was applied is by measuring the leaching fraction. A leaching fraction is the amount of water that drains from a container after irrigation divided by the total amount of water that entered the container during irrigation. The leaching fraction should not exceed 15% at each irrigation cycle. If too much water leaches out, then salts from the fertilizers leach as well, which can pollute the environment and reduce nutrition in the plant. Most container nurseries irrigate daily, except when rain supplies adequate moisture, delivering the water in a single continuous application. Water applied continuously to a container can move quickly through the potting substrate, leaching nutrients in the process. Very little lateral wetting occurs, while a large portion of the water and nutrients are lost through the bottom of the container. In contrast, during the first application of water in a 3-application cyclic irrigation, the foliage canopy and the surface of the potting substrate are moistened but not saturated. Because only 1/3 of the total water is applied at a time, water moves laterally and slowly downward into small pore spaces between particles, resulting in greater wetting and moisture retention than with one continuous irrigation application. The second and third irrigation cycles continue moistening the potting substrate throughout the container. Cyclic irrigation also helps avoid exceeding the water holding capacity of the potting substrate because smaller amounts are applied at timed intervals until the daily water allotment is reached. Compared to continuous irrigation events, cyclic irrigation has been shown to reduce the volume of irrigation runoff and the amount of nitrate leached from containers. Cyclic irrigation can be used with overhead and micro-irrigation, but automation usually is necessary. Field-grown plants usually are irrigated either through seepage or a micro-irrigation system, microsprays or emitters, connected to a water source via a network of pipes. Water from wells and municipal sources usually require minimal filtration for micro-irrigation, while surface water from rivers, ponds, canals, or collection structures often requires extensive filtration to prevent clogging and reduce water flow of micro-irrigation emitters. The irrigation water source and system for application can affect field layout. For example, micro-irrigation pipes typically are laid the length of plant rows. However, long pipes result in reduced water pressure due to friction. Therefore, the field design must consider the irrigation water pressure needed throughout the field. Micro-irrigation water is applied directly to the area where roots are located, the root zone. The water application rate typically is 0.5 to 6.0 gallons in 1 hour. The rate of water application should not exceed the infiltration rate of the soil, so output from emitters and pump capacity must be sized appropriately. When irrigation rate exceeds the infiltration rate, water will move laterally across the soil surface, which may result in runoff. Water infiltration rates for soil textures are given in the table. The amount of irrigation water to apply depends on the evapotranspiration, which is a function of plant size and weather. Plants with large canopies and open space between canopies will require more water than plants with small canopies and minimal space between canopies. It is very important that irrigation water is applied uniformly. Producers can determine the micro-irrigation system distribution uniformity using the procedure given in the University of Florida IFAS publication. Representative areas of each irrigation system having different infrastructure components such as emitters, emitter spacing, pressures, rates of flow, pumps, etc. should be checked every 3 years, and more often if needed. For example, if there's a change to the system. Low uniformities can be due to a number of factors such as improper pipe diameters, too high or too low of an operation pressure, emitters not appropriate for the system design, clogged emitters, changes or wear on the system components, or changes in pump output and pressure. Soil moisture sensors can help to understand what is happening in the root zone of your plant, especially in field production. There are basically two groups of sensors: water potential types such as tensiometers and various forms of granular matrix sensors, and soil moisture sensors that give a percentage or relative content of soil moisture. Tensiometers measure capillary pool of soils at various moisture contents. This device typically consists of a glass or plastic tube with a porous ceramic cup and it is filled with colored water. As water is pulled out of the soil by plants and evaporation, the vacuum inside the tube increases and the dial on the top increases, indicating that the soil is drier. Tensiometers are used in irrigation scheduling to help growers determine when to water. In conjunction with water retention curves, tensiometers can be used to determine how much to water. Although plants require water for growth, too much water around the roots for too long a period of time can cause problems. The problem results from oxygen restriction to the growing roots. The roots have a continual need for oxygen to carry on the process of respiration, which in turn produces energy for growth. When plants suffer from excess moisture, they often exhibit one or more of the following symptoms: wilting of the foliage and succulent shoots, chlorosis of the foliage, reduced vigor, necrosis of the foliage and tender shoots, and death. The degree of expression of the symptoms is dependent upon the plant species and the duration of the flooded condition. In conclusion, there are several systems that can be used, which has their advantages and disadvantages. By calibrating the system based on plant needs, water waste and pollution can be reduced.